Hey there, my name is Alejandro and welcome back for day 33 of me doing the Daily LeetCode challenge until I reach 1 year's worth of green contributions here on GitHub. So today's problem is for August 18th, 2024, and let's get straight into it. Okay, so today we get a LeetCode medium, problem 264, ugly number 2. Okay, an ugly number is a positive integer whose prime factors are limited to 2, 3, and 5. Okay, given an integer n, return the nth ugly number. Okay, straightforward enough. So, okay, n equals 10, output is equal to 12. 1, 2, 3, 4, 5, 6, 8, 9, 10, 12 is the sequence of the first 10 ugly numbers. 1 has no prime factors, therefore all its prime factors are limited to 2, 3, and 5. Okay. So we got to go up to n is equal to 1690. Okay. Okay, so an ugly number is a positive integer whose prime factors are limited to 2, 3, and 5. Interesting. Okay. Okay, sure. This shouldn't be too bad. By the way, first of all, I know that I'm kind of in a weird attire right now and so on. I might look a little messy. Today I had the great pleasure of going on a big hike with my friend Rob in a mountain in Washington called Mount SI, which has like this big like rock scrambling like part at the end and so on, which was super fun. But it took 6 hours and I just got back from it, and as you can imagine, I was kind of starving and so on, but it's like completely pouring rain outside and so on. So I'm kind of having this over here as my dinner. But I didn't want to skip out on today's LeetCode problem, so like here I am and doing it, so on this, and afterwards I'll shower and everything and so on. But it is already late at night, so I want to make sure that at least like before I go take a shower and so on, I have thought of the problem and so on, and here I see it for the very first time. But otherwise, okay, let's get straight into it. My first idea is, well, first I need to figure out like what really is an ugly number. So an ugly number is a positive integer whose prime factors are limited to 2, 3, and 5. So it's not just multiples or powers of these numbers. So clearly 1 is a ugly number, 2, 3, 4, and 5. 6, so why is 7 not? Oh, 7 itself is a prime number. Okay, this is going to give us a little hint about the problem, right? So here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so this example is actually a big hint. Is it just going to be something where it's like... Right, so how are you going to be a prime factor of something not 2, 3, and 5? Either you're the multiple of another prime factor, right? Right, so something like 14 is actually not a ugly number, is it? Okay, so it's not just as easy as is prime, right? It's okay. So prime factors are limited to these 3 numbers. So we gotta think. Like, first of all, like my idea would first of all be to create a function here like called isUglyNumber, right? Self, and it takes a num, right? And then for now let's just return true. And the idea is this, right? So it's like count is equal to 0 while count less than n, count plus or equal int of isUglyNumber, you know, I, where I is equal to 0, I plus or equal to 1, return what, like I minus 1, because if we do count less than n and then this is true, then we increment I plus 1. And then when we get here, count was n, so we want to return I minus 1, right? So it's the idea is kind of something like that. And now it's like we can focus on this ugly number. And maybe there's a more efficient way of doing it. But again, like the idea is like I will likely just have to try to figure out as I try to define, quote unquote, what is an ugly number. So also we have a base case, right? So first of all, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If n less than or equal to, okay, I won't do something like that. So we gotta think about if it's an ugly number, right? So first of all, if num is less than 1, return false, right? So, well, actually, what are these n's going to be, right? So you're from 1. So num is equal to 0, right? So, or num is going to be equal to 1. Is ugly number of num. Otherwise, num plus or equal to 1, num minus 1, right? Maybe you can build off. So maybe we can populate an array of previous prime factors that we've seen, right? So maybe we have def is prime, right? And we take a number. How do we do if something is number is prime? So it's like you go up to find range. Is it math.square root or math.square root? I gotta remember how to do this. So Python 3, is it math.square root of 4? Import math square root. Actually 4 to the 0.5. How is there no math.square root function? Okay, that's strange. Okay, yeah, what square root from math import square root. Oh, square root of 4? Wait, what? Math.square root of 4? Wait, why was this? Oh, I didn't import math. Yeah, okay. So we can do math.square root, right? Okay. Math.square root of num. And if I do int of like 2.6, what does that give me? Okay. 2, yeah, okay. So maybe we do a +1 or +2 because it's this. If I times I. Actually, no. This is this how you do primes? Let me think. What makes a prime number? Right, so maybe like something like this. First of all, if we do something like this for I in range num, then that definitely works, right? So if I do print a string, let's see. Okay. Right, okay. So if num less than or equal to 1, return false. I think 1 is not a prime number. I always forget this, but I think 1 is not a prime number. I remember like arguing about this in high school and so on. So, but I think that's the correct technical term. Which is weird because it's like it can only be divided by itself and 1, but like whatever. Okay, so yeah, 2, 3 are true, 4, 5. Yeah, 11 is true. Okay. Now let's do it this way. It's like, okay, 2, 3, 4 is false, 5 is true, false, true, false, 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 true. Okay, I think this is a correct function for is prime. Okay, so we have a function to determine if something is a prime number. That's cool. We can even return it for to do fix this later maybe. So my idea would be like, as you go through the numbers, populate them if they're prime, and then whenever you go through an ugly number, check them against every other prime number. What are the constraints for this problem? So n is 1690. That's not too big. Maybe you could do some unoptimized stuff. So let's keep it that way. So if it's an ugly number, if n is, yeah. First of all, we could just do assert num greater or equal to 1. So here we're going to have definite. Okay, so I have an idea. Sorry, I'm not talking too much because I'm eating at the same time, but here we're going to do self.primes is equal to an empty array. This is going to be very, very inefficient, but essentially, whenever we want to check if an ugly number is ugly, we're going to loop through all the primes that we've seen, and if it's divisible by any of them, then we just return false, right? But we're going to make it so that if we're going to count primes that are 2, 3, and 5 as not actual primes, which obviously is complete nonsense and so on, but needed for context of this problem. All right, where it's like this will make it so that numbers 2, 3, and 5 are not actually kept as false. So we basically have this function that we wrote called is prime, which tells you if a number is prime, right? So we can just have that. Then we're gonna have this self.primes array. And then it's gonna work for very simply. So we're gonna do for prime and primes, if num modulo prime is equal to 0, that means it is a multiple of that prime number, then we're going to return false. Otherwise, we know it is not a multiple of the prime numbers that are not these ones, right? And of course that it's a positive integer, we assert that num is greater than or equal to 1. So here we return true. So I wonder if something like this works. No. Oh, yeah, lol. Whoa. Oh, self. Yep. Self that is ugly number. Okay. Yep. Yep. And self dot primes. Okay. Let's go. Wrong answer. Okay. Output 10. Okay. Maybe I do I? No? Right. Alright, so I'm getting the n+1. So maybe we do something like this. Oh, okay. Now is it just... Am I not populating this correctly? Okay, you know what? We're gonna do this. We're gonna do self.ugly numbers is equal to an array, right? And here we're gonna say while length of self.ugly numbers is less than n, if self is ugly number this, self.ugly numbers that append num, right? And here we're gonna return self.ugly numbers at index, and we want the nth, right? So n-1. Output 1. So here we're gonna do print self.ugly numbers. That's a problem. Oh. Lol. Num plus or equal to 1. Okay, so 1, 2, 3, 4, 5, 6. Okay, 7 should not be in there. Yeah, if self dot is prime. No, yeah, we don't actually use the prime stuff, right? We don't populate self dot primes left yet. So if self dot is prime num, we're gonna do self dot primes dot append num. Now, there we go. Very nice. Now, given that we have a working solution, but still it might be too slow. Maybe not, just because n is very small here. But this is one way I would think of solving this problem. So I think this is correct. It's just it might be too slow. Yeah. Okay. Okay. Which makes sense. Right. Okay. So you gotta do something more clever here. So we're worried about something like 14, right? What's special about 14? Basically, we don't want things to be multiples of previous primes that we've seen. I mean, one way to do this problem is to compute all ugly numbers by first computing all prime numbers. Well, even then, it's too slow, right? Sorry, I'm just eating as I think, but I'll make myself very clear in terms of my ideas. Okay, so we've essentially found a way to basically solve this problem. It's just too slow, right? Kind of like yesterday. Well, I hope I don't take 5 hours again here, where we found a solution, but it was too slow, and so now we have to work on making it faster. Okay, sorry. Just one last sip of water and let's get straight into this problem. Okay. Okay, so this was my idea, right? An ugly number is a positive integer whose prime factors are limited to 2, 3, and 5. So what we're going to do is populate the ugly numbers one by one, which is like I'm going to have a self.ugly numbers array. Whenever I find a number that is an ugly number, right, I'm going to append it to my ugly numbers array and keep increasing num and so on until I get n ugly numbers and then return that nth ugly number, right? So that's kind of the idea. And so the way I do this is I have this is ugly number function, right? And so how does this work? I basically say like, hey, loop through all the previous primes you've seen so far, right? So every time I call is ugly number, I first check if num is a prime number. If so, then I append this to the primes and I automatically return false because I know that like it is not a multiple of 2, 3, and 5 because I actually, in my is prime function, I do something incorrect where it's like if the number is less than or equal to 5, I actually return false even though 2, 3, and 5 are prime numbers just because it's like I don't want to include these, right? So that's kind of the idea. And so I populate this primes array, right? And then I say, okay, for each prime in self.primes, which don't include 2, 3, and 5, if the number I'm given here is a multiple of any of the previous ones I've seen, then return false, right? Otherwise, return true. So I'm trying to think, so how could we make this more efficient? Maybe it's like you could use the result from the previous ugly number to get the next ugly number, right? So maybe, maybe one thing you could do is when you populate self.primes, we can keep populating prime numbers, right? Ooh, this might be interesting. So what if we populate prime numbers? So the first one we know is 7. When we got 7, that means we have 1, 2, 3, 4, 5, 6 ugly numbers, right? And then we can say like, okay, first of all, if n is less than or equal to 6, boom shakalaka, we have found our solution, right? Otherwise, we start from 7. And then we find the next prime number, right? So it's 8, 9, 10, and then we get to 11, right? And how many numbers are in between there? So 1, 2, 3, right? Which is just, what's 11 minus 7? This is equal to 4. So cur prime minus prev prime plus 1, right? So the next prime is what? 12, 13? Is 13 a prime? Yeah, right? So between 11 and 13, there's only 1. So 13 minus 11 is equal to 2. Oh, do you want to do minus 1? No, this doesn't work, does it? 8. So 7, 8, 9, 10, and then I got to the 11. So with 11 and 7, 11 minus 7 This gives me 4. So yeah, I want minus 1 to actually give me 3, right? And so yeah, 13 minus 11 minus 1 will give me that 1 of just having 12 in there, right? Very nice. Okay. I see. So we can do something like that. We can do something like, okay, I'm cooking here. Okay. I like this idea. So, well, obviously that's going to be way more efficient, not in the sense that we're still going to go number by number and compute primes, but in the sense that we're not going to go for every number and then loop through all the primes that we have seen, whereas just that's going to become a bigger and bigger computation over time, right? So that might be very nice. So we know whenever we see a prime number, okay, whenever we see a prime number, recent most ugly number is that prime minus 1. And we know there's at least 1 per space, right? Because the evens are divisible by 2. Okay, this is very cool. Okay, this is going to be very nice. Yeah, it would be nice to have a list of all the primes. I don't want to cheat in the sense where it's like I run like is prime like a couple times on my machine and get like the list of all the primes and then just have them ready for computation here on LeetCode. That would be kind of hilarious. Because I mean, this is bound for 1690. So in terms of solving the LeetCode problem, I can just pre-compute the values and boom, no problem, right? Whenever, but yeah, I think that kind of takes away from the heart of solving a LeetCode problem. If I really get stuck, I unironically will go resort to something like that. But for now, because of the problem normally as expected, then I think that's better. So yeah, so this, I just have to keep track of the previous ones, where it's like, maybe I just keep it as an array, where it's like, I'll just, yeah, well, I can just keep it like that. So, is prime, is ugly number. Maybe I just do it is prime. Note this function also populates self.ugly numbers. It does not just check if num is prime and that alone. Okay, so we're going to modify as prime, where essentially, maybe we should keep track of some like distance variable, right? Where it's like we always keep track of self.prev prime. We can start with 7, right? So, we can start like this, right? 4, 5, 6. Right? So that's fine. We're gonna comment this out. We're gonna comment most of this out. Equals 8. We're gonna start from 8. Yeah, we can start from 11. We know that's the next prime, right? Just to make things nice and easy. Okay. The idea here is I'm kind of cheating in the sense that I'm populating the first 6 which are very obvious here, keeping 7 as my previous prime, and like I'm starting from 8, right? As if though I just got 7 as my previous prime. Blah. Or it's like just to make the logic a little easier for me here. It's fine to pre-compute some values as long as I don't pre-compute everything, you know. Num is equal to 8. We're gonna say while length of self.ugly numbers is less than n, populate if prime num, return self.ugly numbers of n minus 1. Oh, this is gonna be so beautiful of a solution. So chef kiss. Okay. Oh, I'm excited. Okay, this is gonna be my brilliancy at work here. This is gonna be great. This is gonna be very great. So we're gonna populate if prime self is prime num, right? Actually, we're gonna keep this logic here, and we're gonna keep a helper that was called def is prime self comma num, which is gonna keep that logic, right? We're gonna, of course, we're gonna ignore 2, 3, and 5, right? So that's the idea. Actually, we're straight up gonna say assert num larger than 7. Start problem with prev prime as 7 by default to make life easier. There we go. All right. Bada boom, bada boom, bada boom. For iron range, yeah, it's fine. We can just start from 2. Actually, we have to, right? We first have to check if the number's even, right? So we actually can't skip that. For iron range 2, the square root num plus 1. If num moduli, we're not even gonna need that. That's gonna be so beautiful. Like literally, chef keys. It's gonna be so great. Okay, I like. Let me cook here. I'm gonna code up a solution here, and I'll explain it. I promise. This should work, by the way. This is gonna be nice. Yeah. So we can get rid of that. Yeah, so for iron range 2, method square root of num plus 1, if margin I is equal to 0, return false, return true, right? Okay, so we have a helper is prime, right? So now here in my beautiful populated prime function, first of all, I'm going to say is prime equals self.is prime of num. Beautiful. Chef kiss. If not, actually, sorry, I'm just gonna do if not self.is prime, return. Otherwise, we've got a beautiful prime number up our hands here. We're gonna populate essentially for ugly number. We're gonna say ugly numbers. We're gonna change that to ugly nums. For ugly num in range, self up the previous prime plus 1 all the way to cur prime is equal to num, cur prime, but of course not inclusive. We're gonna say self.uglynums.append ugly num, right? We can just move this in here. That's fine. If it's not prime, just return early. Otherwise, there we go. It's gonna work, no? Self.populate is prime. And then we're gonna say self.prev prime is equal to cur prime. And then Okay, first of all, let's run. Uh-oh. Not good. I have a beautiful infinite loop here. Oh. Well, maybe that's why. That would explain some things there. Oh yes, this works. This works. Let's see. Let's see if it's fast. Okay. Okay, I got a little too happy there. 14. Why is 14? Ooh. Right. Okay. So I don't include cur prime. I didn't get rid of the issue, did I? Well, yeah, from 13, 14 is not prime, 15 is not prime, 16 is not prime, 17 is prime. And then you can't just add all those numbers in between, because 14 is 7 times 2. But then if I loop over the previous primes, my solution is no better than before. Maybe if can I just check for the previous prime? But then no, right? So because 14, so 7 times 3 is what, 21? Then if I check for the previous prime of 11, it'll be like, or 13 or whatever, it'll be like, oh yeah, bro, you're totally good. Yeah, that's not cool. I mean, maybe self dot primes equals this. Prev prime so we start off with 7. Prev prime is equal to self dot primes -1. Self dot primes that appends cur prime, right? For prime in self dot primes if ugly num modulo prime is equal to 0, continue. So something like this might work, but again, it might be too slow. First of all, let's use the test case. Yeah, so it works there. Yeah, self.n. Okay, this might be too slow, right? Let's check. We getting slow down in here. Okay, yeah, so we don't get around the previous trick, right? It's what sucks is having to compute if it's a multiple of any other previous prime. How can we shorten that calculation somehow? Maybe I create a ban list, right? Ooh, that might be good. That might be good. Ooh, that might be good. Ugly num, not in ban list. Self dot ugly nums. Let append ugly num. So I do self dot ban list here. Is equal to a set. So first of all, let's run this, and I expect the last case to fail. Okay, cool. Now populate else. So what, okay, so here's my idea. The problem here is that we're looping through all the previous primes in order to check like, oh, is it multiple of that prime? So like, for example, like 21 is a multiple of 7, right? So that one is bad. It's not an ugly number. So what we can do, this might be a bit bad, but we can say add to ban list every multiple of num, which is prime, up to 1690, since that's constraint on n. So for band num in range, so you want, first of all, you want this. So I just, let's say I just found 7, right? I just found 7. Okay. So first of all, we're not going to have self.primes. We're going to self.prev prime is equal to 7. The only thing is that this set might be way too huge, right? But I hope it's not because of the 1690 constraint, where it's like you can hold like 30, 40, 50,000 elements, I hope, in a set like in Python and not be too bad. But okay, it might start getting a little tricky. Also, the bigger the prime, so like what's so 7 modulo, so 1690 divided by 7. So okay, so that one will have 241 entries, right? So if I do equals L equals I for I in range from 7 up to 1690 inclusive by a range of 7. L. So yeah, 7, 14, 21, 28, 35, 42. So I have every multiple of 7 all the way up to 1690, right? So here, my idea is like, again, so for ban num in range, so from the current prime, self.max num, none. Max num self.n. So all the way up to max num. Actually, this might make more sense, right? If I just do self.n, that'll be more understandable. By an offset of cur prime. So by the way, what this does is like start from cur prime all the way up to the last number and jump by the number cur prime every time, right? So that's why it's like you start from 7 and you jump by 7 to 14 to 21 and so on. So we're going to add a band list as a set. And so then whenever we're about to add an ugly number, we go, whoa, 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 whoa. Is it in the band list? And what's nice about the band list is that like if I get a number like 21, well that one will have been included from this band range from like integer 7, right? And so band list dot add band num. First of all, let's run something like this. Oh, this is not gonna work because yep. Prev prime equals self.prev prime. If length of self.ugly nums. First of all, this is just a syntax, so it's like if it's greater or equal to n, then return, right? Just return early because then we can get to here and it's like, oh my gosh, it's greater than n, or greater or equal to n. So there we go. So just return early if that's the case. Then yeah, so at the end here we want to have self.prime is equal to cur prime. In self.n, of course. And I shall wait in order to hit the run button. Ban list. It's supposed to be self.ban list. I will wait. I have waited. And this one's wrong. Why, my friend? Why? Ooh, because I didn't do it for 7. Okay, lol. 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 Set of we can start off prev prime at 0. Actually a -1. So in the first iteration we'll start from 0 all the way up to the cur prime. So that's how we'll have 7. And here this num, we'll start it off at 0. Actually, we'll start it off at 1, right? If num less than 7, return false. Whoa. What have I done here? Oh yeah, I should get rid of these now. Why am I starting from 0? Maybe this should be 0. Right, start from 1. Okay, so now that one thinks it's still 14. Okay, otherwise I will start it off like that. Print self.banList. Self.ugly numbers. Ugly nums, yeah. Sorry. This will be a more accurate representation. Okay, so here I have 7 in the band list. Wait. 7 should not be the only one in the band list. No, I'm not doing it up to 1690. N is, yeah, okay. But should I need it up to more than 1690? So let me think. First of all, I can try something like this for now. Or surely this is enough. It's not even enough. Okay, I'll do 1690. What? Oh, yeah, low. This should work. Yeah, so this or 1690 plus 1. Let's just do that. First of all, let's just try to run this. Although, yeah, okay, printing this might not be the best. Although we get a straight up wrong answer. Okay, we're gonna do 1690. Okay, we do pass it. What's wrong? Whoa, okay. Okay, where are we printing? Stop printing. All prints are going to be stopped with hashtag print. Let's do that. Now submit. Okay. So, maybe I should populate the primes all the way up to self.n, right? But that's what I'm doing. I'm stuck at 1691. Which is, of course, this value that I'm coding in here. There's like one is too big, right? What is too big? How many coprimes am I gonna have to fit in, right? What is my range of ugly numbers? My range of ugly numbers is insanely high, right? N is equal to up to 1690. But ugly numbers, the fact that there's gonna be primes, right? You know what? Let's do this. Is prime num. It's gonna be the. We're gonna create a new function. If num less than 2, actually return false. Line range 2 comma int square root num to the 0.5 plus 1 modulo I equals 0, turn false, turn true. Port math, def is prime num. If num less than 7, return false. Line range 2 comma int math dot square root of num plus 1. If num modulo I equals 0, turn false, turn true. Okay. L equals this. Num equals 7. Well, length of L less than 1690. Self dot is prime num. L dot append num plus or equal to 1. L dot append num plus or equal to 1. Jeez, so that was actually very fast to compute. So these are the first 1690 primes. Wow, okay. And we can use some information like that. That would be cool. Band list to set num and L. This is just too much though. I mean, you can run this and try submission, right? But band num is going to be too huge now. Maybe 400 times self.num. And just keep trying. I mean, I'm just gonna, like, at some point I'm gonna reach an optimization point. I'm gonna binary search my way, like, oh, if 400 fails, then try 200, otherwise keep going up and so on. I mean, this is a janky hack, but it's like, I'm kind of not realizing how far I should go, right? Oh, so that's not accurate enough. So let's do 600, right? What's 1690 divided by 2? Let's do 846. Let's try that. Time limit exceeded. Let's give 700 a shot. Well, yeah, this is probably not gonna get. I'm not even close to the 596 case, right? And this is like n is equal to 339. Yeah, I'm not getting there. Oh yeah, they're just gonna keep doing. Yeah, they're just gonna keep going crazy. They could have like 1690 test cases, if anything. Yeah, this is a good idea, but then again, it's like it takes a while to add this into into the ban list. So let me think. How far do you want to go, right? You want to populate the first n ugly numbers. So you want to do this at least. You want to do this at least self.n times. So really what you want here is cur prime times self.n. But is that even gonna... Alright, let's just do this for the sake of sakeness. Okay, wow, that doesn't even work. Donk. Yeah, at that point, like... Yeah, you want to do this self.n times, right? That's essentially what I did want. But you're saying that this is not enough? Interesting. So that's not enough. Wow. Yeah, I'm a little stuck, not gonna lie. Like, it's all about computing whether a number is ugly efficiently, right? I thought I found a cool trick with being able to populate them in distances between the prime numbers that you find. But then again, you run into the same issue as before. Okay, maybe let's look at some of these hints. I think that's a good call. The naive approach is to call is ugly for every number until you reach the nth one. Most numbers are not ugly. Yeah. Only the ugly ones. Most numbers are ugly. Oh, did they try to trick you at the beginning? An ugly number must be multiplied by 2, 3, or 5 from a smaller ugly number. Two, 3. This is a multiple of 2. Multiple of 5. This is a multiple of 2. Multiple of 2. Multiple of 3. Multiple of 5. So, okay, I did think of this. I just like, I was like, because one of my first ideas is essentially like multiply like 2 by 2 by 2 by 2 until you get to 8 and then realize that that's like 5 and so on. And then you're like, oh my goodness, well, 5 would have been a small number. So like the next prime number will be like 5 times 2 and so on, and which is like 10. Or 3 times, like you understand what I'm saying, right? And right, so you can okay, I don't want to look at any more hints for now, but that's a very good one. So we could go down like some kind of tree where it's almost like a 3 children tree. Oh, you know what would be a really cool solution? We start off with like a root node 1. And then there's 3 children from that 1. You can either get to 2 or to 3 or to 5. And obviously, when you have a tree, you can do DFS in order traversal to get like kind of the in order version of that thing, right? But then obviously it's like this will be an infinite tree where it's like for this 2, you're gonna have 2 times 2 is 4. 4 times so 2 times 2, then this times 3 is what, 6, then times 5 is equal to 10, then this 3 here, sorry, let's do this. This 3 here is gonna be like times 2 is 6. Ooh, okay, but we're gonna have duplicates here. Times so we can also do a DFS, but we keep track of a scene set. So yeah, 3 times 3 is 9. 3 times 5 is 15. Then from here, it's like we do a 4. So 5 times 2 is 10. Times 3 is 15. Times 5 is 25. Okay, so there's some recomputed work here, right? It's like 4 and 2. So maybe here we can get rid of the 6. Okay, so we could do something like we get rid of the 6 here. So here, this is an X. Here we can get rid of the 6, so we do 4 and 10. Or we can actually do 4 and 6. Then here we can keep 9 and 15. Here what, 10 and 25? No. So there's 4, 6, 9. 9 only appeared in here. Just bizarre. Okay, this tree is not going to be populated in a nice way, right? But, okay, if we do the keep tripling approach, though, we know that at some point you start with 1 node, then 3, then 9. So you can specify a max depth, right? And you're going to hit a max depth real fast. But actually, you're going to have a lot of duplicate numbers, right? So, We could end up throwing stuff inside a list and sorting it. So maybe we start off with a num thing. Here we do like I times so maybe we can do something like, yeah, we start off with 1. Then we're going to do the 2's list is equal to 2. I times 2 for I in the list. 3's list is equal to I times 3 for I in list. Then 4's list is equal to, or 5's list. I'm kind of mad that I didn't think about this before. I actually did think in my head, but I shut up and didn't say it because I was like, oh no, we're in positive integers, right? Not just like multiples of these guys. And so, okay, well, sometimes you gotta actually go with an idea because it turns out to be correct. So whenever you think of something, try it, because oftentimes your intuition is right. I think I've heard something like that, where it's like in tests, where it's like if you think of a multiple choice answer and then you end up thinking of another one, go with the one you first originally thought, because your intuition is often right on things. And so, yeah, I had good intuition in this problem. I just shut up because I was like, oh no, actually no, right? But sometimes you should just listen to your intuition. So if you have an idea, try it, especially since it's a LeetCode, where trying really is totally okay to do. So that's a little upsetting, but okay, at least we can continue from here. This is going to be very inefficient, but I'm trying to find a way to get this to work. Right, so we're just gonna call this old. We're gonna come here into okay, that was an old idea. We're gonna start off with ugly num set, ugly set with the number 1 in it. Bigger set, ugly set, prev ugly set is equal to this, prev is equal to ugly set. Sorry, bless me. Or yeah. Bigger ugly set equals ugly set. First of all, we're going to do something like this, but we're going to try. Well, length of bigger ugly set is this. Equals set of 1. First of all, we can see if something like this works. Oh yeah, this stuff is obviously not allowed. But I only change it here. Alright, because it's pointers. I hate that Python does pointers. That does not work. Output 25. Oh, because these are not in order? Maybe you have to do something like this. I had 4, 5, 6. So I skipped out on 8. Where does 8 come from? So 2, 4, and 8, right? So I skipped, yeah. I skipped it. So yeah, I like the tree idea, but maybe there's something. Okay, let's just look at more hints. I'm just gonna. The key is to maintain the order of the ugly numbers. Try a similar approach and merging the three sorted lists L1 and L2 and L3. Okay, and L4. Let's say, assuming you have the kth ugly number, then UK plus 1 must be min of L1 times 2. So it's like 4, 6, and 10. So it's like. So the idea is that the twos list would be 1, 2, 4, 6, and 10. And then you have 1, 3, 6, 9, 15. Here you have 1, 5, 10, 15, 25. It's like if you pick with the 1 here, then you get rid of it here, but you also get rid of it here. Get rid of it here. Then you pick the number here, you get rid of 2. That's like, okay. And then 3. You get rid of 4. Get rid of 5. Okay, I get it. Yeah, let's restart. So I kind of understand. So twos list. Twos, threes, fives equals 1, 1, 1. while length of 2's is less than n. Right, because it could be just you get everything from there. So yeah, okay, this is useful. Then this makes sense, right? So while length of 2 is less than n, new 2's equals twos plus or equal I times 2 for I in 2's, 3's plus or equal I times 3 for I in 3's, 5's plus or equal I times 5 for I in 5's. We're going to replace that with num. There we go. Assert length of 2's equals length of 3's equals length of 5's. Assert length of 2's greater or equal to n, but that should always be true. Then ugly nums is equal to this. Two pointer, 3 pointer, 5 pointer equals 0, 0, 0. Then we're going to say length of ugly nums is less than n. Otherwise return ugly nums of n minus 1. Then we're going to say, okay, ugly num is equal to min of 2's at 2 pointer threes at 3 pointer, 5's at 5 pointer, ugly nums dot append that ugly number, and then we're going to say if 2's of 2 pointer was ugly num, two pointer plus or equal to 1, update pointers. So it's going to be 3 pointer. Oh, like in basketball, lol. It's going to be 5 pointer. It's going to be 3's. This is going to be 5's. Maybe return something like this. What? Ugly nums. One, two, three, 4. Maybe we should do something like this. 1, 2, 3, 4, 5 works. Oh, but you can't add each other, right? Yeah. So you'll never mix is the problem. Okay, let's read these hints. So what's L1 and L2 and L3? Most numbers are not ugly. Try to focus your effort on generating only the ugly ones. Okay, sorry, I'm hyper focused. Turn 1. So this says 1, 2, 3, 4, 5, 6. Doesn't include 8 somehow. Twos, comma threes, comma fives. Ugly nums. Ugly nums. Ugly nums. I'm gonna have to create a copy. 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 So 2 comes from from a smaller ugly number. The key is to maintain how the order of the ugly numbers. What is this magic L1, L2, and L3? This is not even related to K. What the heck? Right, so we can negative number is a positive integer whose prime factors are limited to 2, 3, and 5. Okay, so 2 covers you all the even numbers. Yeah, the problem is that like I'm not reaching deep enough. It's like I'm doing a breadth first search when I should be doing like a depth first search where it's like I keep adding. It's like this tree, right? Where it's like you start off from 1, right? And so obviously the next smallest is to do 2, right? Or like you have these options 3 and 5. Then from 2 you have like 4. You can go to 4, or you can go to 6, or you can go to 10. You know, here you can go to 6, 9, or 15. Here you can go to 10, 15, 25. But then it's like, if I populate with these, right, even if it's sets, it's like this 8 number is actually smaller than even this 9, 15, 10, and 25 business. So I have to somehow consider this every time. So it's like, when I have 2, 3, and 5, right? Man, this is hard. So I have 1, 2, 4, 6, 8. So like I could populate the evens. But then it's the mixtures that suck, right? Ah. Ooh. I could do something like, so maybe I do smallest 2 is equal to 1. Smallest 3 is equal to 1. Smallest 5 is equal to 1. And then it's like, the next one is either smallest 2 times 2, 3, smallest 5 times 5. And then how do I get the mixtures, right? Yeah, smallest 2, that would give me 2, but then it's like, if I multiply that by 2, I get 4, which is smaller than 1 times 3, right? It's just, how do I get 8? Well, 2 times 2 times 2. How do I get something like 6? I need 3 times 2 specifically. I'm getting to an idea here, where it's like maybe I need to introduce being able to multiply by anything. This is tricky. So like I'm thinking, like if you multiply 2 and you get to like 8. 8 is no longer good, or you get to like 4. 4 is no longer good. Yeah, so you have 3 and 5. It's like, how do you generate 6? Or smallest 2 smallest 3 smallest 3 times smallest 5 smallest times smallest 5. Still, this is complicated. Interesting. Yeah, I wish they gave a better hint on what these L1, L2, and L3 sort lists are. That's what I'm trying to figure out. Maybe this is a good time when I take a shower, I think for a little bit. I come back from the shower, maybe have some brand new ideas. What if I do something like that, right? I don't want to spend something like 5 hours like yesterday's problem and so on, where it's just I keep trying to hit dry walls, where it's like even here when I open all 4 hints, I'm still like a little bit stuck, where it's like I know I'm thinking towards the right direction. I think the most useful hint was this, where like this brought me back into the right direction, where I actually thought of doing this at the beginning, but I quietly closed myself off thoughts-wise because I was like, no, that's dumb, because of the positive integer constraint. But yeah, I'm gonna have to think a little harder about that. So like, why don't I take a shower, right? Think about it a little, and I might not have something up when I come back and so on, but maybe I can cook up some new ideas. So, because I do feel like not too clean and so on, because I did come from the hike and all that. So yeah, I'll just take a quick shower. I'll come back and I'll see if I've cooked something up, up to my recipe. So let's see. I'll be right back. So see you in 1 second. Hey there. So sorry about that. Nice and showered now. That's great. Let's take a look back at this problem. I will admit it took some time. So instead of thinking too deeply about the problem, I think I forgot a little bit of it. What were we doing over here? An ugly number is a positive integer whose prime factors are limited to 2, 3, and 5. Create an integer and return the nth ugly number. Right. 1, 2, 3, 4, 5, 6. Oh, yeah. We were looking at the hints, right? Yeah, okay. An ugly number must be multiplied by either 2, 3, or 5 from a smaller ugly number. So this is the useful hint, right? And so, okay, here we were trying something. It's like the key is to maintain the order of the ugly numbers. Oh, I remember now. Okay. So we were here at like 1, 2, 3, and 5. So the problem is, so I think that this is a bit misleading, right? Where it's like, if you do the smallest 2 times the smallest 3, no, if you do smallest 2 times 2, you're always going to get 2, 4, 8, right? Okay, so let's think about this. From 1, we populate 2, 3, and 5, right? Then from 2, 3, and 5, we populate, what do we populate? So essentially we have 1. So we know we're going to get 1, 2, 3, 4, 5, 6, right? That's the beginning. So let's think about how we do this. We'd have 1 here. And like we know that's the starting case. So from 1, we populate 2, 3, 5. But we know that we are going to need to slap in 4 in between here, right? So we shouldn't be adding these values directly. So we need to like commit to 1. Okay. We need to commit to 1. Sorry. Okay. Okay, so sorry about that. I was texting my girlfriend. That's priority number 1 in this world, so forgive me. 1. Okay, so we were talking about 1, 2, 3, 5. Okay, so the problem here, right, is like we need to populate 4 before we populate 5, right? And then when we get to this 8 here, right, so we can't just go from 1 to... Ooh. Can you? No, you can't. Okay, so what I was thinking is like you take so from 1 you populate these, then you take the minimum 1 and you multiply by 2 because the smallest between multiplying 2, 3, and 5, right? But then it's like you'll only have even like how will you get to something like 9? At some point, so the whole problem I'm struggling with is the mixing part, right? Or like for example, like how do you get to that 6, right? Where it's like if I just do like 1, 2, 4, and then I'm like, oh, 8 is smaller than if I did 3 times 2, so get 6. Like for example, if I keep multiplying by 2, I will never reach 25, right? So I can't always select to multiply by 2 on and on and on. I need to select multiplying by 3 and 5 from some times to time. So it's like, okay, I had this 1 and I populated it with 2, 3, and 5. Wait a minute. I have a 1. I take that 1 and I populate these values. Okay, what if we apply that idea recursively, right? We take this 1 and we apply, almost like we're taking that element, adding it as our first result, and then we have 2, 3, and 5. So that's like candidates, right? We'll say 2, 3, and 5. Oh, but you're gonna have a no. Okay, with duplicate numbers, we can always just keep a scene set, right? So that's not a problem. So I'm worried about like, you know, like 4, 6, and 10 is the same as 6, 9, and 15 here, or the 6s are the same and the 15 here is the same. So okay, we can avoid that with a scene set, right? Okay, so let's say we take 1. Okay, so what if we take the smallest element here, like 2, right? And from it, it's like we generate these values, right? So we know 2 is the next one. So we want 1, 2, 3, 4, 5, 6, and then skip 7, right? So then from this, we get rid of 2. So goes from getting rid of 2, so we have 3 and 5. And now we get these next candidates. 4, 6, and 10. Okay, this isn't necessarily always sorted. Because, yeah, okay, here we have like 3, then 4, right? Or 5 and 4, sorry. So 3 is the smallest element, but then it won't be 5 and 4. So we can't use a queue. Oh, but we could use a heap. I'd have to think about the complexity of that. Okay, so let's think about this. The next smallest in here would indeed be 3. If we get rid of 3, that means we keep 5, 4, 6, and 10. We add 3 here, and then we add what? 6, 9, and 15? 6, 9, and 15. But we only add things that we have seen, maybe? So, like, we don't add 6. Oh. We could do something like this. This would work, no? Then what, you like pop 4? And so from 4, yeah. Oh my gosh, wait, this is gonna work. Okay, 2, so 4 would go into 8, 12, and 20. Okay, we don't get there. But yeah, we're getting this 8, we're getting this 12. This is perfect, dude. Wait, okay, let's try to... oh my gosh, okay, I have a lot of code here. Let's try to code something like that up. Okay, wait. Okay, I want to... maybe this idea doesn't work, but it should, right? Do I get everything? So I'm always... so it's like I'm... I don't know what they mean by like 3 sorted lists here. Yeah, they don't talk about using a heap in here. I mean, we could try it. Like the thing is that, like, will I get all possible? Like, okay. An ugly number must be multiplied by 2, 3, or 5 from a smaller ugly number. I'm just generating new possibilities of multiplying by 2, 3, or 5, right? So like these, okay, these are not necessarily previous ugly numbers, but they're derivations. They're possible candidates which stemmed from these, right? So 1 times 2 and 3 are not there, but the 5 is there. From 2, you had 4, 6, and 10. 4, 6, and 10 are all there. And 3, you have 6, 9, and 15, which are all there. So it's like, yeah, you essentially, you're keeping track of the, I think this will work. We can just try it. We can just try it. Okay, so let's do this. So how are we gonna do this? So we start off with what? 1? Yeah, 1. So we're gonna say ugly nums is equal to 1. We can keep that. We can, okay, so let's get rid of all this. Okay, so maybe we call this candidates, and ugly numbers is going to be equal to empty. While length of ugly nums, okay, so this is going to be a min heap, right? So, okay, while length of ugly nums is less than an n, okay, here we're just going to return while ugly nums of, we don't even, just add -1. While length of ugly nums is less than n, so what do? We can, okay, so we're going to pop this, right? So, okay, so heap q dot heap pop candidates, smallest candidate is equal to this. Then for new candidate in, okay, say smallest candidate times 2, smallest, okay, so this times 3, and then smallest candidate times 5, we're gonna say heap q dot heap push candidates, come on, new candidate. Right, here we didn't have to heap q because we just have one element, so that's good. Heapify, I mean. Smallest candidate equals, we heap pop. Now that's us popping the 1, right? So here we're gonna do self dot, ugly nums is equal to dot append, actually. And here we're appending them in order. Oh, mate, okay, dot append, okay, so, okay, I don't want to get too excited here because, okay, I'm pretty sure, okay, for new candidates and these new possible candidates, we're going to add that to the heap again. First of all, okay, let's just try running this first of all. Okay, it's wrong. But why doesn't work? Here I'm just off by 1. 10, 15, 24, 50. No, I'm off by a lot. Why? Two, 3, and 5. 3, 5, 4, 6, and 10. Oh, wait, we need to keep track of a scene set, right? So we can't. If new candidate not in scene, this, right? Here we're going to keep track of a scene hash set. Scene.add smallest candidate. Actually, no, we want to prevent them. So this is going to be equal to the 1. Oh my gosh. Okay. Okay, let's get rid of this print. Submit. Okay, there we go. Bravo. Okay. Okay, it works. Okay, perfect. Okay, so we can just oh, that's so okay. See, shower time equals best time. You get to think clear and all this. Sometimes okay, lesson well learned. It's good to take a break sometimes. Okay. Okay, this is cool. This is cool. Okay, okay. And this won't be too hard to explain either. I can even keep this here. Okay, 47%. Okay, we range and so on, so we might get to the. I don't know if this will be optimal solution though. Yep. Oh, 37%. Okay. Okay, doesn't matter. I'm just glad to have a solution, so that's what matters. Okay. Okay, wow. Okay, nice. Well, okay, that's essentially the solution. It's like I'm shocked at myself, right? Okay, well, very nice. Turns out I guess I just kind of overcomplicated the problem myself, where it's like, yeah, so first of all, lesson well learned, like, it's always very useful to like identify a goal, go through a case, and identify what you need, right? So like in my case, it was like I'm stuck about like the mixing the numbers. And it's like, okay, I know that the first 6 or 8 are this way, right? So somehow I'm gonna have to make a decision for populating 1, and then populating 2, and then populating 3 and 4 and 5 and 6 and so on, right? So that's why I kind of had this logic here, where it's like, okay, I know at the beginning the first number I need to populate is 1, and obviously I start with 1 and so on, and then it's like I'm gonna populate 2, 3, and 5. But then between 2, 3, and 5, I can't add this directly into my list, right? Because that wouldn't make sense, even if I keep them in the sorted order. I'm missing a 4 here, right? This I need to get in there, which means that before I consider, like, before I add all of these elements, I need to start considering, like, new possible elements I could add. Now the problem is I was fixating myself on like taking 2 and only multiplying it by 2 to get this 4. But what if I just take this 2 and instead see all the 3 possibilities that can arise out of it, right? Which would be like populating the 4, 6, and 10 and so on. And then I kind of realized that earlier, but then I was like, oh, how am I gonna like search this as like a DFS tree and so on? But the idea is that like you can just create a min heap and like keep track of the smallest result at every single step and so on, and that's like how you're gonna get them in order, right? Like you're trying to build this in order, so always like pop the smallest one, see the 3 new possibilities that can come out of it, and bada bing bada boom, just keep doing this until you have the first set numbers. So as a quick summary and recap of what I did, so the problem was an ugly number is a positive integer whose prime factors are limited to 2, 3, and 5. Given an integer n, return the nth ugly number. What you had to realize was basically this hint number 2, right? I actually kind of don't know what they're talking about here with these sorted lists and so on. I guess I just didn't know. Okay, so maybe that's why I'm getting the 35%, and there's just like a better solution. So okay, but I didn't get it, but I got a solution on my own that's different, but hey, it works, so that's good. Otherwise, the hint that was really important is just an ugly number must be multiplied by 2, 3, or 5 from a smaller ugly number, right? Obviously, we start from 1. We know that 1 is kind of, we know that this is the first like 10 ugly numbers, right? So like this always stays the same. So we start from 1, and then from then we can like multiply by 2, 3, and 5. Again, we're kind of told by this hint like we can just multiply by 2, 3, and 5, and like from any smaller ugly number, and that's like new possible candidates for smaller ugly numbers. But obviously we kind of want them in order, right? So that we return the nth ugly number. And one of the big problems I was having is if you just keep populating elements, even if they're not in order, until you reach like, you know, like n and so on, and then return the nth smallest, that doesn't work because there might have been some smallest elements that you skipped and so on. So that's why I kind of chose this strategy. So I'll explain. Where it's like, okay, the idea is, sorry, I'm rambling a lot, but the way I solve this problem is obviously we want to get the nth ugly number. We start from 1, and from what we're going to do is we're going to consider we're gonna start off building a min heap, starting with just the number 1, right? We have this as our starting point. We know that that's gonna be the very first ugly number, and then every ugly number that we find from that, we know is gonna be a previous ugly number that we have found, either multiplied by 2 or 3 or 5, right? So that's the idea that's set in stone into our minds. Now the way I did this is like, okay, we start from 1. Let's construct a min heap such that at the beginning we just have 1 and we're gonna pop 1, right? And then from this one, like that, we start from this one, we're going to populate 3 elements out of it, right? One where we multiply the number by 2, so that gives us 2 because 2 times 1 is 2. One where we multiply the number by 3, and one where we multiply the number by 5, right? Again, from hint 2, we have that an ugly number must be multiplied by either 2, 3, or 5 from a smaller ugly number. We know that 1 is the smallest and very first ugly number. So from 1, we know we can generate the numbers 2, 3, and 5 by multiplying 1 by each of these numbers, right? And now here is the secret sauce trick, all right? Ready, boys? Okay. And gals, you take the minimum out of these 3 that you knew generated, right? Or however many you have, but for now we just have 3. So these are kind of like our candidates, right? Where we start off where at the beginning we have nothing, and our candidates, so ugly numbers, at the beginning we have nothing, and the number of candidates that we're considering is nothing, right? So this is none, this is none, right? Now we start off with the number 1, right? So we know that we have 1. So essentially we start off with candidates here, and then we pop 1 and we have none and so on. But the idea here is that you start off with 1 as the ugly number, right? And then your next candidates are 2, 3, and 5, right? And you got that from taking this 1 and multiplying that by 2, 3, and 5, right? Because those are the next 3 new ugly numbers that you can generate. Not necessarily the next 3 ugly numbers, that's the important thing to realize, but 3 newly generated ugly numbers that you can use to derive every other ugly number from then on. And so here you want 2, 3, and 5 as your new possible candidates. Now again, what you want is you want to find these ugly numbers in sorted order, right? So since you have 1 here, the one that's going to come after it, right, is going to be the smallest of all the candidates, right? Which in this case happens to be 2. So what we can do is get rid of 2, and from 2, get 3 ugly numbers that we know are reachable from 2, right? Which are 4, 6, and 10. So to our candidates array here, we add 4, 6, and 10. And then we keep track of this 2, right? And then we want the 3rd ugly number, right? What's going to be the 3rd ugly number? Well, we know it needs to be the smallest one of our possible candidates again, right? Which in our case is 3, right? And from 3, what can we generate? We can generate 6, 9, and 15, right? 6, 9, and 15, and we add 3. Now, there's only one caveat here where it says, like, when I add new numbers to this candidates, it must be a number that I have not seen before, right? Otherwise, I'm going to end up having something like 4, 5, 6, 6, and so on, and da-da-da. And it's like, well, obviously you shouldn't have the same number of times like inside of ugly numbers, because like this will mess up with your indices, right? You should only like consider an ugly number once and so on, because you want the nth ugly number. So it's like the nth unique ugly number, right? So that's why whenever you add elements, you're going to only add ones that are either not like you have not seen before and like specifically not been in candidates, or an ugly number. So it's like if a number is in candidates or ugly number, sorry, then you don't want to consider, right? So here 6, we don't consider it because we already have 6 over here, right? And that's how we keep them unique. That's what I do with the scene set. Where it's like for every new candidate I consider, if it's not in scene, then I add it in scene, and then keep q.heap push it, right? And so that's kind of the idea. Again, it's like 1, 2, 3. What's the next value that's going to come after 3? Well, we take the smallest out of this candidates array, which is 4. From 4, so we're going to put it into the next ugly number. From 4, we know that we can reach 8, 12, and 20. So we're going to add 8, 12, and 20, which are all unique and so on, and keep populating this candidates array over and over and over. And we're going to keep doing this one by one until we reach the nth ugly number, right? And then once we reach that, we just return the nth ugly number. So the way I work this in my code is like, this is my main heap, my candidates array, right? So this guy right here. My ugly nums is like these ugly numbers that I'm generating that I start off as empty. And then my scene set at the beginning of, I just say, hey, I've seen the number 1 because I'm about to pop it anyway, right? And so I say, well, the length of this array is less than n, right? So until it's greater or equal to n, in which case I have at least n unlucky or ugly numbers. Because I'm populating one by one, I'll have exactly n. So even if I did -1 here, like my solution should still work. I mean, we can confirm it here. But yeah, so but ideally it's just like keep going until I basically haven't found the nth ugly number, right? Because we're going to keep adding the newest ugly number every single time in sorted order, and so once we get to n, then we have the nth ugly number, right? So here we say, okay, smallest candidate is heap heap hop candidates. I get the smallest number from candidates, and then I say like, okay, I'll append that to my new ugly number. So I start off with appending 1 to my ugly numbers, and then I generate the 3 new possible candidates, 2, 3, and 5, right? But again, the important trick is to notice that these are not the next 3 necessarily. They're just 3 possible future smallest, smallest candidates that you might consider putting into next in the sequence of ugly numbers, right? But that's why the beauty is to just use a min heap, because it's like, well, just get the best possible candidate you have at any single step. You generate new candidates every single time that you add a new number to ugly number, but otherwise, always take the very best, or in our case, the very smallest candidate that we have available to us. And then again, we just, if it's not in scene, right, we only consider things uniquely once. Heap queue, heap push, and so on. And by the way, for heaps, like heap pop and heap push are just log n operations. So this is very, very nice. So this is actually going to be n log n solution. Okay. So maybe there's like a linear time solution and so on, but oh well, like n okay, yeah. Yeah, technically that's better and so on, but yeah, so I'm proud of the solution. This is a good solution. So I hope that makes sense, at least, where it's like we keep populating ugly nums until there's at least n numbers so that we can return the nth ugly num, and we do it quote unquote in sorted order by utilizing this heap trick, right? Where we realize that whenever we generate new candidates, they're not necessarily in the order that they should be added to ugly nums. So we use a min heap to leverage the fact that we only want to add the next like smallest candidate and so on, so that we get the ugly numbers in quote unquote sorted order, and then return the n smallest one. So I hope that explanation kind of makes sense. We can just resubmit one last time here without these comments. And yeah, so that's about it. And yeah, otherwise, in case you want to do something similar to what I do, the extension that I use is called LeetSync. I trust this extension, but by no means does this mean that you have to trust this extension yourself. Essentially, what these guys do is whenever you press the submit button here on LeetCode, do a quick demo here if I come into my LeetCode repository. So this problem was called ugly number 2. So you'll see that I just submitted just now, and it'll put a copy of the README the very first time you submit the problem correctly, and every time you resubmit the problem with new code, it'll just put the submission here. So just very, very useful extension in case you want to do something similar to what I do, where you keep track of your solutions here on GitHub. Or for me, like for example, my goal is just to get like 1 year of these green contributions. No, wait, did I miss a day? No. This was yesterday. I submitted something yesterday. Is it because I submitted past midnight? No, that has to be a joke. Okay, I mean, I can move on from something like that. Oh, but that's so sad. Okay, you can barely notice it. Oh, but that's so sad. No! Oh, it's because, yeah, yesterday's problem took me 5.5 hours, right? So I submitted after midnight. There's no way right now. Or no, it's today. Right now it's past 12 a.m. Oh, it's actually today that I messed up, where I didn't submit something until past 12 a.m. So it just says that I didn't submit. I should have done this. I should have submitted something 30 minutes earlier. I should have taken forever in the shower. No. Okay, otherwise, that's a big shame. That's a rip, but okay. I mean, worst case, we just keep going until we get another New Year's worth of contributions. Like, that'll be okay. But otherwise, like, even if I get this, like, you know, like, pushed over here, if I miss one day, that's fine. So we kind of already have tomorrow's, but I'll still do tomorrow's problem and so on, of course. And so, but yeah, that's a bummer. Okay, I need to make sure that I finish the problems before midnight from now on. So that's a little bummer. Otherwise, okay. Oh, I mean, what can you do, right? So, what can you do? Otherwise, that's kind of it for today's video. Otherwise, I hope that my explanation made sense. And in case you want to use an extension like this, like in case you do, I'm just showing you my setup in case you do want to do something similar. But otherwise, that's pretty much it for today's video. If you didn't find this if you did find this content enjoyable or useful to you in any way, I would highly appreciate if you left a like or a comment. I will make sure that I respond to every single like and comment. Oh, well, every single comment that is left on my channel. So if you want me to have a conversation with you, like, please leave a comment and I will be like more than 100% willing to talk to you. I want to hear what you guys are all about and so on, what's inspiring you to do LeetCode or even watch my videos, or even if you have feedback for me and so on. I want to hear it all. But otherwise, I will just catch you in the next time that I do a LeetCode problem. And so until then, ciao ciao my friend, have a good rest of your day. Bye bye.